In the last lecture, we had looked at spherical tensor operators. Well, we had really looked at in detail at spherical vector operators, which are spherical tensor operators of rank 1 or corresponding to spin 1 states. We also said that by analogy, we should be able to extend this to all spins. That is, we can talk of higher rank spherical tensors such that the commutator with J3 of Tjm is mh cross Tjm, which is basically mimicking this relationship, and this is J plus minus acting on Tjm raises or lowers the m index in Tjm by 1 with a factor in front, a familiar factor, but it exactly mimics this relationship. And we had also seen that the reason behind this is not really very difficult to understand. Just like J3 and J plus minus are operators which act on the states Jm of the vector space, add J3 or add J plus minus are quote unquote super operators which act on the operators Tjm, and all we are saying really is that Tjm's are eigenstates of the operator add J3. Remember, the action of add J3 on an operator is simply commutator of J3 with that operator, and the action of add J plus minus, which is of course the commutator with J plus minus on the same operator, essentially reflects the same algebra as the original J3 and J plus minus did. So of course, since the action of J3 and J plus minus on these states really the consequence of the way these states change when you rotate your coordinate system, we do expect a similar kind of situation with the operators themselves. So let's just take a look at that. But before we do that, let me just remind you of this general situation which we have been talking about several times during the course of these lectures. Under a rotation of coordinates r, and we are going to consider passive rotations here. For active rotations, all that happens is some signs change. For a passive rotation of coordinates r, a ket psi could be Jm, but doesn't have to be. Psi changes to psi goes over to ur acting on psi, where ur is some operator corresponding to the rotation. In fact, if the rotation happens to be a rotation through an angle theta about an axis n hat, then this ur turns out to be the exponential plus I theta by h cross n hat dot j, and that acts on the state ket psi. Just to point out once again, this plus sign in front of the I theta by h cross n hat dot j here is a result of using passive rotations. For active rotations, which many books use, you would see that the operator for rotations ur is given by exponential minus I theta by h cross n hat dot j. So this change in sign would usually be a case when we are talking of active rotations as opposed to passive rotations. But this is how states change. Well, we could instead of saying that states change when you rotate, you could actually get the same result by saying that operators change when you rotate. So an operator O goes over to ur dagger operator O times ur. Just to remind you, this is to ensure that ultimately the physical results that we need, which depend on the way matrix elements change when you do a rotation, that is the same in both these approaches. In one, the ket changes; in the other, in this one, the one we are talking about now, the operators change. So of course, given the fact that ur is given by this operator here, you get exponential minus I theta by h cross n hat dot j or exponential I theta by h cross n hat dot j. This actually may look a bit neater, or it would be easier to follow the arguments if we made use of the more advanced notion of capital AD and small ad operators that we talked about in the last lecture. So basically, this whole operation is the same as the operator capital AD corresponding to this minus I theta by h cross n hat dot j acting on O, which, as we have seen in the last lecture, is an exponential operator, or rather an exponential super operator. exponential of minus I theta by h cross n hat dot add j acting on the operator O. Now, specifically when we talk about angular momentum eigenkes, they of course transform the same way as any states do. So, the state Jm gets acted upon by this operator, exponential operator acting on Jm. But since we know the action of the operators J3, J plus, J minus, which make up this n hat dot j, on the state Jm, it should be possible for us to calculate exactly what this operation is. And we have seen that this essentially gives rise to a matrix. The matrix corresponding to the operation R of rank j, and these are the m prime m elements of the matrix, dj m prime m R acting on j m prime and summed over all m prime. All you are saying is that this state is going to be a state in the vector space, and since the subspace of all states spanned by the states Jm for a fixed j, but the 2j plus 1 different values of m, is an invariant subspace under rotations. When you rotate such a state, you get a result which is a linear combination of all such states Jm prime. And the matrix that you see sitting here are nothing but a matrix made out of the coefficients of this transformation, of this expansion of the rotated Jm in terms of the Jm prime. Now, notice that the operator which is acting here, exponential I theta by h cross n hat dot j, is very similar to the operator which is acting here. There's one change, of course, there's a minus sign. So, spherical tensors on which the action of J3, J plus, J minus via commutation, or rather add J3, add J plus, add J minus directly, is perfectly well defined. In fact, it is defined exactly the same way as the action of J3, J plus, J minus on Jm, should show exactly similar behavior under rotations. Similar but not exactly the same. Why? Simply because of the minus sign here. So, basically, for a given rotation R, what happens to the states and what happens to the operators, apart from the fact that for operators is the add j operator which is acting, not j, apart from that, there is this minus sign which means that you will get an inverse action. So, notice the fact that add J3 acting on Tjm is mh cross Tjm, add J plus minus acting on Tjm is just this Tjm plus minus 1 with this factor, and this exactly parallels J3 J plus minus acting on Jm. So, just like under a passive rotation, Jm becomes dj m prime m R Jm prime. What happens to operators? What happens to the Tjm operators in particular? Well, this is the operator which goes and acts on Tjm. So, this, remember, is what we have been calling a super operator, an operator which acts on operators to produce new operators. But just to point out, add J3, add J plus minus acts on Tjm exactly the same way as J3, J plus minus do. The only difference here is one of a minus sign here, which means this is an inverse of this operator in some sense. So, basically, what will happen is the mathematics will completely mimic the case for states, and you will end up with dj m prime m R inverse acting on Tj m prime times Tj m prime. The only difference here is you have the inverse rotation here than the R here. That is the only change. Of course, because these matrices are unitary, dj m prime m R inverse is actually the inverse of dj m prime m, and because it's a unitary matrix, there is a small change between dj m prime m R and this one. All that happens is you get a conjugation and a transposition, which means the m and m prime indices have been switched. So, this is the way in which Tjm transforms when you rotate your coordinate system. It transforms almost the same way as the states, eigenstates Jm do, but the transformation has a small difference. At the level of coefficients, is the difference is you complex conjugate the coefficients and switch the two indices. Perhaps it's even better to understand it this way, that instead of the rotation r, you get the coefficients corresponding to the rotation r inverse for Tjm. That's it. Otherwise, the transformation of Jm when you stage Jm when you carry out a passive rotation of coordinates exactly mimics the transformation of the spherical tensor operators. Now, there happens to be a set of functions, a pretty familiar set of functions, which mimic exactly this behavior under rotations. They are the functions which we call spherical harmonics, which remember are what you get when you take the Lm eigenstates, L of course for integer L, the Lm eigenstates, and take the position representation, that is, you take the overlap of these Lm eigenstates with the position eigenvectors, and you end up with Ylm theta phi. Now, what happens when you carry out a coordinate rotation? The eigenket with which you are taking the superposition, this ket r, that changes to ur of r. That's the way kets change. And so, what does Ylm change to? Instead of taking the overlap with ket r, of course, when you take the overlap with ket r, you are taking the first forming the bra corresponding to ket r, then letting it act on Lm. You will take the bra corresponding to urr. That's of course r ur dagger. But however, ur dagger acting on Lm is of course inverse of ur acting on Lm. So that's exactly the same behavior that we saw for Tmj. Just one notational point: when you write Ylm, you typically write the L below and M above. That's a standard convention, and we have been following the convention that the J index for spherical tensors go above and the M index go below. But apart from that, this is just a notational, small notational matter. Other than that, this is an exactly parallel relationship to the one we saw before. And this gives us a very nice way or nice trick to find out some new spherical harmonics for ourselves. So, for this, what we do is define some operators. Well, curly y Lm, which is an operator whose eigenstates are the position eigenvectors, and the eigenvalues are essentially Ylm theta phi functions, but with an extra r to the L thrown in for convenience. You will soon see why is convenient. So, upon rotation of coordinates, this operator changes to ur dagger Ylm ur, and you expect its eigenvalues to change to r to the L y tilde ml theta phi. And this essentially means that you are going to end up with a relationship like this. The same case, remember, when you are talking of passive rotations, you can either say kets change, operators don't, or you can say operators change, kets don't. So, here the ket r has not changed, the operator has changed to this ur dagger Ylm curly Ylm ur, and as a result the eigenvalues have changed, and this immediately tells you, using the fact that y tilde Lm is essentially a superposition of Ylms Lm primes with these coefficients, it actually tells you that these new rotated operators are simply a combination of the old ones. There is a typo here, this should be an M prime. So, Ylm primes combine with these coefficients to produce the rotated versions. Of course, this is exactly the same transformation as the transformation for the spherical tensor operators of rank L. There are 2L plus 1 of them, one for each value of M, of course. So, let us give an example of this. Let us start with L equal to 1 spherical harmonics, which should be pretty familiar to most of you. So, y1 minus 1 is this thing. These factors in front are of course normalization factors, which ensure that when you take the mod square of this and then integrate over all possible angles over a spherical volume element, you end up with 1. So, these are the 3 spherical harmonics corresponding to L equal to 1. So, from them we can create the curly y operators. Curly y 1 minus 1 will simply be y 1 minus 1 times an extra r. So that's all there is to it. An extra r here in all the three of these. They have one extra r each. But the advantage of putting in the extra r becomes clear when you think in terms of Cartesian coordinates. After all, e to the minus I phi is cos phi minus I sin phi. So this is r sin theta cos phi minus I r sin theta sin phi. And if you remember the connection between polar coordinates and Cartesian, it's easy to see that this is simply x minus I y. Similarly, this r cos theta is obviously z, and this thing, well, you can do it again, but it's easy to see that this is just the conjugate of this expression. So you get x plus I y. So this is the thing in terms of Cartesian coordinates. Also, now that you are talking of these as operators, which operators has the eigenvalue x minus I y? Of course, the operator x hat minus I y hat. I am just not writing down the hats, but you can just translate this to the operators that we want by regarding these coordinates as operators, which we always do in quantum mechanics in the position representation. Now, this was for the position vector, where the three components of course are x minus I, x and y and z, but this would generalize immediately to a very familiar result. If you drop this common factor of root over 3 by 4 pi from all three of them and replace x, y, z by three components of any three vector operators vx, vy and vz, you immediately get these three, which you should realize is nothing but the standard connection between Cartesian coordinates, Cartesian components of a vector operator vx, vy, vz and the spherical vector counterparts. So this spherical harmonic trick just reproduces that connection. Just to remind you once again, the difference between these expressions and these ones is that this is more general. After all, the way in which these y1 minus 1, y1 0 and y1 plus 1 will behave under rotations depend on how x, y and z behave under rotations. And just like x, y and z, just the same way as x, y and z behave under rotations, vx, vy and vz behave exactly the same way. That's why they are vector operators, or they are components of a vector operator, which is why if you make the same combinations, the combinations will work exactly the same way. So that is the reason why these are spherical vector operators, which of course we knew already. To get an inkling of something which we have not seen before, let us take a look at the L equal to 2 spherical harmonics. These again you can easily find in any textbook, or you can remember that they are basically the PLMs times e to the IM phi's with normalization factors thrown in. I am not saying you have to memorize them, but you can recreate them if you want to. So these are the 5 L equal to 2 spherical harmonics corresponding to m equal to minus 2, minus 1, 0, 1 and 2. From here, going on to the curly y's is simple. All you do is multiply each one of them by an extra r, so r square rather, out of the L, remember. But once you do that, you should realize that r square sin square theta e to the minus I2 phi is simply the square of r sin theta e to the minus I phi, which we met in the last slide, and r sin theta e to the minus I phi is just x minus I y. Similarly, you have r sin theta e to the minus I phi, which is x minus I y, and r cos theta, which is z. And proceeding this way, this one, of course, if you push in an extra r square, you get 3r square cos square theta minus r square. So that's just 3z square minus r square. These two, apart from a change in sign between y2 minus 1 and y2 plus 1, are just conjugates of what you had before. So it's pretty straightforward. So these, when you regard x, y, z as operators acting on position wave functions, these give you examples of rank 2 spherical tensors. So you can immediately construct rank 2 spherical tensors out of this. X minus I y whole square is of course x square minus y square minus 2y xy and so on. and you can easily find out all these 5 tensor operators, which essentially have quadratics in x, y, z. In fact, this is going to be very, very important when we try to find out expectation values or matrix elements of quadratic functions of x, y, z, which we will often need to. You can take a look at these tensor operators, find out which possible tensor operator combinations we are talking about, and use that in a big way to simplify your calculations a lot. That, after all, is one of the major reasons why we are at all studying spherical tensors and so on. Now, of course, this is because you are using x, y, z. What if you were using vx, vy, vz? It would go similar, in a similar fashion, except for one thing. Well, x square minus y square minus twice i xy is the square of x minus y iy, simply because x and y commute. Otherwise, you would have xy and yx. In a similar fashion, if you just clear, because general vector operator components don't commute among each other, the expressions can be written down directly from here, but with a bit of caution. So, in fact, I have made a mistake here. The T2 minus 1 and T2 plus 1 should have extra factors of 1 by 2. The 1 by 2's come in because we are just using Vx minus Vy Vz and Vz in the other order. Of course, if we were using x, y, z which commute among each other, these two would be exactly the same, but in general they are not. Just like here, instead of twice I xy, I wrote I xy, I Vx Vy and I Vy Vx. We have done the same thing here. I have forgotten to throw in an extra half. That extra half should be there, and this gives us a way of creating second rank spherical harmonics if I start from a general Cartesian vector set of vector operators. We will see in this in more detail now when we talk about the general rule for combining spherical tensors. Just to remind you, we define spherical tensors through the action of the add j operators. Now, add j has this property, it's called derivative property. When it acts on a product of two operators, that's really j vector commutator with AB, and this really has nothing to do with something very esoteric. It's just the way commutators behave. If you take the commutator of say j with AB, you get j times commutator of, or sorry, a times commutator of j with b plus commutator of j with a times b, which we have just written down as a at jb plus at jab. Why is this called a derivative property? Because this is exactly how derivatives act on product of functions. Remember the u dv dx plus v du dx thing? The d dx acts first on one factor, and then you have another term with d dx acting on the other. Exactly the same thing happens here. But notice the way the angular momentum operator, the total angular momentum operator, acts on a direct product space or direct product vector is simple. It's very similar. Remember, we said that j is j1 plus j2, but we meant j1 cross i2 plus i1 cross j2, and that means there will be one term in which the angular momentum operator acts on psi1 with psi2 left intact, another term with psi1 left intact and j2 acting on psi2. With this, you can just think about it a bit, and you should be able to figure out that the way in which combination of spherical tensors work is very much the way in which addition of angular momentum works. So, just like you can combine j1, j2, m1, m2 states, which are eigenstates, remember, of j1 square, j2 square, j1z, j2z, to form invariant irreducible subspaces which are irreducible under rotation, which are eigenstates of total angular momentum j square and jz, though these are of course eigenstates of j1 square, j2 square, j square and jz. Remember, we use rounded ket symbols just to remind you that these are eigenkets for the whole thing and these are eigenkets for the direct products. And You can expand this in terms of these with the coefficients which we have spent a lot of time upon in previous lectures. These are the Clebsch-Gordon coefficients. So just like you have this, how would tensor operators combine? Exactly the same way. xj1 m1, if x were a set of 2j1 plus 1 operators corresponding to a spherical tensor of rank j1, and y corresponds to 2j2 plus 1 operators corresponding to a spherical tensor of rank j2, and combine them together, multiply them, of course in the sense in which you multiply operators, multiply them by these coefficients which are just complex numbers, either we can choose them to be real numbers as you have seen, m1 m2 jm, and sum over all m1 m2, and you end up with a tensor operator of rank j corresponding to the mth component. So you can combine spherical tensors to form new spherical tensors using the Clebsch-Gordon series. Just to point out, the 2j1 plus 1 coefficients components of x combined among themselves when you rotate your coordinate system. The 2j2 plus 1 components of y do the same. What happens to the products? They are, of course, when you form all possible products of xj1 m1 and xj2 m2 for fixed j1 j2, then you get 2j1 plus 1 into 2j2 plus 1 different operators, and when you rotate, they of course combine among themselves. So the direct product of states and direct product of operators work exactly the same way, and just like the direct product states, they form an invariant subspace but not an irreducible one. So you can reduce them to their irreducible components by the Clebsch-Gordon series. That's what we did earlier with states. We can do exactly the same thing with operators. Just to illustrate how this works, let's take a look at how to combine two rank 1 spherical tensors. First, let me remind you that if you added 2j equal to 1 angular momenta, you will get a bunch of Clebsch-Gordon coefficients which are pretty easy to understand in terms of just the expansions of the jm eigenstates. So these are the j equal to 2 eigenstates. You can work all of them out yourself, it's pretty straightforward, or you can just look them up in a table. Of course, when I say these are the Clebsch-Gordon coefficients, I mean the coefficients are just the non-zero ones are the ones you can see here in front of the states here. These are the j equal to 2, but then of course when you add two j's, each one, you get j equal to 2, j equal to 1 and j equal to 0. So j equal to 1 gives you this and j equal to 0 is this combination. So these are the corresponding angular momentum addition results, and these are the corresponding Clebsch-Gordon coefficients. So how can we form use these results to form combination of two rank 1 spherical tensors, which are of course just spherical vectors. So let us say we have two spherical vectors u and v with components, of course, u11, u12, u10, u1 minus 1, and v11, v10, v1 minus 1. So how do you form, say, second rank tensor? Of course you can't, when you form the second rank tensor by combining these two, by multiplying these two in some sense, you don't get one second rank tensor, you get 5 of them. There have to be 5 components to a second rank spherical tensor. So T22, just let me point out, T22 has to be exactly parallel to this. There's only one Clebsch-Gordon coefficient here, which is 1, sitting in the front of the state m1 equals 1, m2 equals 1. Remember, the j1, j2 indices, which are both 1, have been suppressed on both sides. So this is the left hand side is really 1 comma 1 semicolon 2 comma 2. Here is 1 comma 1 semicolon 1 comma 1. So m1 1, m2 1. Exactly the same way, T22 will be Clebsch-Gordon coefficient of 1, u11, v11. Now if you want to write it in terms of Cartesian components, you know that u11 is just minus ux plus iuy by root 2, and minus, this one is minus vx plus ivy by root 2, and you multiply them together, and this is what you end up with. By the way, we have already seen this before. In the special case when we used ux, both u and v as the same operator, you would end up with ux square minus uy square minus I ux uy plus I uy ux, which is exactly what we had a while ago. Well, what is T21? Just let me go back to the Clebsch-Gordon coefficients here. 2 1 would be 1 by root 2 ket 1 0 plus 1 by root 2 ket 0 1. For operators, this will be 1 by root 2 u 1 1 v 1 0 plus 1 by root 2 u 1 0 v 1 1. So, let us go back to that. This is T21. That is exactly what it is, and once you supply the components, you end up with this expression, which again with v equal to u gives you exactly the T21 expression that we had a while ago. By the way, there we had T2 we started with T2 minus 2, then gone on to T2 minus 1, T2 0, T2 1, T2 2. So, if you are comparing, please compare the correct expressions. Don't get confused with the minus sign in T2 1, and you didn't have any minus sign in the second expression, but that was for T2 minus 1. Similarly, T2 0 can be easily figured out. Same Clebsch-Gordon coefficients 1 by root 6. There you had 1 minus 1 plus 2 by root 6 0 0 plus 1 by root 6 minus 1 1. Just completely go parallel to that, and once you put in the expressions for each one of them, it's pretty easy to see that this is the expression you're going to come up with. I'm not bothering to work out the other two, they're pretty straightforward, and you can almost completely write them down just from what you had already done. In fact, you can write them down from what we have already done, and these are the two extra components. So, this is how you combine rank 1 spherical tensors. Of course, in terms of spherical tensor components, the expressions are just this here. These expressions are really the more complicated looking expressions are really in terms of the Cartesian components of the vectors. So, if you are really dealing with spherical components to begin with, the expressions are actually a lot simpler. Well, this is how you get rank 2 spherical tensors out of 2 rank 1 spherical tensors, namely 2 spherical vectors. How do you get rank 1 and rank 0, which is also what you are supposed to get? Well, rank 1, again look up the Clebsch-Gordon coefficients or look up the expansion. The 1 1 eigenket of Jm was 1 by root 2 1 0 minus 1 by root 2 0 1, and we are just doing the same thing here, just following that, replacing the Jm's J1 M1 J2 M2 by T J1 M1, in this case U J1 M1 V J2 M2 and so on. Now, if you expand this out and do the calculation, you will notice something rather funny, which is apart from an I by root 2 factor, now this is an algebra which you should carry out yourself, it's pretty straightforward. You actually get things with these components should immediately remind you of there is a cross product, and you actually get u cross v's x component plus I times u cross v's y component divided by root 2. But remember, this exactly is a spherical vector corresponding to the Cartesian vector given by u cross v x, u cross v y, u cross v z. And this is not an accident. In fact, it's not a one-off case. For T1 0, you get exactly the same thing. For T2 0 or T1 minus 1, sorry, you get I by root 2 times u cross v x component minus I times u cross v y component by root 2. This, of course, is an algebra which you should carry out yourselves, and which obviously says that there is a cross product of u cross v hiding here. This is nothing but a spherical version of the familiar cross product. So, even if we had never known the cross product before, we could have discovered it here at a rather advanced setting. When you are trying to combine two spherical vectors to form a spherical tensor, this is what you get. By the way, we have been focusing on spherical vector operators and spherical tensor operators. basically because we are using this in quantum mechanics. But spherical vectors, spherical tensors are useful wherever rotations are useful, wherever you have rotational symmetry, which means the same thing comes up over and over again in various other places like acoustics, like electromagnetism, and so on. So when you are going to do advanced electromagnetism, you would definitely need to use spherical tensors, not spherical tensor operators, but spherical tensors. But the algebra here is very similar. Well, now that we have the cross product, can the dot product be far behind? The answer is no. The dot product is almost here. In fact, it is the one which we have not talked about so far. I talked about combining two spin 1s to get a spin 2 tensor operator, then a spin 1 tensor operator, 3 components, and we are left with a spin 0. And the spin 0 version turns out to be minus 1 by root 3 u dot v. Again, a calculation which you should carry out on your own. So we have seen basically how to create your own spherical tensors out of spherical harmonics. We have also seen how to combine lower rank spherical tensors together by forming products with special coefficients weighting them, the Clebsch-Gordon coefficients, so that you can form spherical tensors of higher rank. Now, the obvious question that should be in most of your minds is, what's the good of all this? I have already given you a hint about that. In many cases, you may need to calculate matrix elements of complicated operators, especially in angular momentum eigenstates. So, matrix elements between two different angular momentum eigenstates. And angular momentum eigenstates, by the way, are very good ways of describing physical systems where you have spherical symmetry. In all such systems, calculation of these matrix elements become much simpler if you can recast them in the language of spherical tensor operators, because there happens to be a very nice theorem which tells us how to calculate these matrix elements. This theorem is called the Wigner-Eckart theorem. It's one of the most important theorems in the theory of symmetry in quantum mechanics. In fact, it actually is a more far-reaching theorem, not just in rotations. It's useful for many other kinds of symmetries as well, but we will be of course studying just the rotation version. In the next lecture, we will talk about the Wigner-Eckart theorem. We will briefly outline its proof, but more importantly, we will show you how to use this to calculate matrix elements, which we are going to use in many calculations. So, bye for now.